So, as you have seen, the title is quite difficult to read, so there is plenty of words. And so I will try to explain the concept separately, starting from the end. So the first thing is, what do we mean by large-scale application? So this is a broad definition of it. In this current era, we have a lot of data currently that is generated by different fields, like finance, biology, astronomy, and so on. And it enables us to elaborate realistic and complex models. So for this talk, we'll assume that we have a continuous function that is associated with this model. And computing this function is quite a challenge because it's expensive, and so we want to use parallel resources to compute it faster. But also because of the limited amount of memory, we cannot fit all the data all the time in the memory, or it's difficult to, it's limited resources. So for this talk, we will also assume that we want to compute the gradient of this function. And it can be for optimization, like maximum likelihood, or minimization of an error. So this is what we mean by large-scale application. This is an example of it. So in evolutionary biology, we want to test hypotheses of molecular evolution. And for that, we are using DNA and also phylogenetic trees. So this is a phylogenetic tree. It's kind of the history of the species, as you can see, how they evolved through time. And concerning the DNA, you can see that we have more and more DNA. So this is the amount of DNA that has been sequenced during the last years, the last 20 years. And you can see it has, if the marker won't work, so it has grown quite a lot. So this is an example that I will use all during this talk. So now what about derivative acyclic graphs? So we have already heard a bit about them previously in the previous talk. But so the idea is for us to represent computation as a graph. And here you can see we have some parameters. And these parameters, we will use them to compute the function. Here we have a partial results that need these parameters. And here is the final result. So the edges are representing the data dependencies. If we go back to our example, we have here the phylogenetic tree, and there is underlying computation to this phylogenetic tree. So this is the DAG that is behind this phylogeny that we're going to use to compute, in this case, the likelihood, which is going to be the top node. And this is, for instance, the computation that are associated with this DAG. So you can see this is matrix computation, or matrix exponentiation, and so on. So this is just for an example. So now we know what is a DAG. And the last thing that was in the title, or nearly the last thing that was in the title, was the finite difference approximation. And so the idea is to compute the gradients using the finite difference method. And as you can see, we have the function that has a set of parameters. You have d parameters, and we're going to use a small positive scalar, which is a perturbation. I will call it a perturbation for the rest of the talk. And we apply that to each of the parameters one by one to approximate the partial derivatives. So the difficulty is that we have to compute d plus one function. And so it's to compute the full function, which is here, and then each of the perturbed function. So now coming back to the title, we know what it is about, but for the scheduling part, which is going to be the subject of this talk. So first we're going to see two scheduling problems, one for a sequential computation of the finite difference approximation, and then a parallel scheduling that will arise when we will want to use multiple processors. Then we will see some experiments where we use this method, and we will see what's the performance gain that we will have. And I will finish by a conclusion and some perspectives. So just let's go back to the graph. The idea is to see how we can compute this sequence on this graph. So the first thing that we can do is a naive approach, where we're going to compute first the full graph for the first function initialization, for the whole set of nodes. And then for the first perturbation, we will do again the same thing. And we will do that for all the function evaluation. And this is where it's really not efficient, because it costs d plus one function evaluation. So let's try to be a bit more clever. and reuse partial results that are in the DAG, and also use memory to store that. So for instance, we first compute the first function, so we compute everything, and we store a copy in memory. We then can compute the first perturbation, so let's assume that there is only this node that is affected by the updated parameter. It means that we only have to recompute the set of nodes, like the parent of these nodes, so the nodes that will be affected by the updated computations. Then we can use the copied memory of the DAG in memory to restore to the previous state in order to compute then the next function perturbation. So this is more efficient, but the problem is that you have to keep a second copy of the DAG in memory. And as I've said at the beginning, sadly, we don't have enough memory since we had to load a lot of data and the amount of partial result can be quite high. So we'll try to solve this problem by using recomputation. And I will show you how it looks like. So again, we compute the full function. And then we compute the first update. I will call that an update. And then we have to compute the next update and to recompute these nodes to put them in the previous state. So instead of reloading from the copy that we had before, we're going to just recompute this node to put them back to the initial value of f of x. So for the remaining of the talk, I will call that a reset operation and that an update operation. So we can see that the scheduling problem will arise now, because in this case, we were having these two nodes that were affected by the updated parameter that were quite locally placed on the DAG. But if it was not the case, you can see that the amount of computation can be bigger. So depending on let's say the locality of the updated parameter, the cost will be different. Before continuing, I will just introduce some notation. So let's say that we update the parameter xy, so we perturb this parameter. The set of parameter that we have to recompute is going to be psi, and the cost to do this operation is going to be c of psi. And then when we have the reset and the update operation, it's the same. We have two sets, but the computational cost is going to be the union of these two sets, and the cost will be the cost of the union of the two sets. So we're going to rewrite this first sequence of evaluation, and we're going to use an arbitrary ordering. So instead of taking the perturbation in order, we're going to use any possible ordering. So we can see that first we have to compute, so by rewriting it, first we compute x0, and x0 represents the function evaluation that is here. Then we do the first update, starting from x0, and then, so this represents this term, and then what we're going to do is to start from x1, do the reset operation, so remove what we have computed before, and add the new perturbation, which is going to be an update. And we do that until the end. The associated cost is the following one. So you have the cost for the full, the full computation, then the first update, and then the reset plus update operation. So what we want to do now is to find this ordering R that will minimize all these costs. So this is the first scheduling problem. We want to find the ordering that will minimize this equation. So the problem is that there is d possible permutation, meaning that there is d factorial possible orderings. So I will not go into detail into that, but the idea is that we wanted first to see what could be the impact of the schedule, and under some condition, under the case where all the cost of all the perturbation is significantly greater than the cost of one full function evaluation, it will lead to a 2x faster computation if you have a good schedule, and in the opposite case, 1.5 times faster. So it's not enormous, but it's still important. So if we rework a bit this expression, we can remove this cost because it's independent of R, and if we include this one within this sum, like you can see here, in fact, we can see that this problem ends up to be equivalent to the traveling salesman problem. So the traveling salesman is, for those who don't know, is the idea of finding the shortest path going through a set of cities by going only once to each of the cities. And so here it's similar because we have this cost function that can be seen as a distant function between two perturbations. And so what we want to do is to find the paths that go through all the gradients that will minimize this cost or distance function. So this is a really nice result because it means that we can use any kind of software that have been developed for the TSP and the knowledge that has been that has been researched on the TSP. So now we have the first scheduling problem, and we're going to look at the second one, is the one when we want to use several computational resources. And so now the new problem is that we want to take, again, this sequence of function, and we want to partition it to a set of P processors. So these tasks have an heterogeneous cost, meaning that we cannot just cut this function and send like an homogeneous amount of computation to each of them. We have to take into account these facts. So it looks like the independent task scheduling problem, which is also a well-known problem, but it is not, again, because the cost of a task depends from the preceding computation. Since we have this reset operation that we have to do before computing the update, like the computation of a new perturbation, it depends on the previous task. So xy will depend on xy minus 1. It means that each of the partitions must have a good ordering to be kind of efficient. The ordering is important. And when we swap tasks from one set to one partition to another partition, we have to, again, assess the ordering of each of the partitions. So it's going to be quite expensive in terms of computation to guess the best schedule, the best partitioning. So in the end, what we want to do for this second scheduling problem is to combine, we have to combine the partitioning in P subsets, so for the P processors, with the optimal permutation of each of these P subsets. Okay, so just to give an idea, this is the cost that each of the partition will have. So the first is really similar to the first problem. You have the first full computation, then the first update, and then the reset and update part. For the other processor, it's going to be a bit more different. They don't have to compute this full function, but they still have to compute for the initialization. But what they can do is to merge the first update operation with the initialization to reduce the cost. So one idea that the first thing that we would want to do, would be to minimize this overall cost. So this would be the first potential scheduling problem that we would think of. But this is not really like the best solution because this only guarantees you to have the minimal overall cost, but not the minimal computational time. The minimal computational time is limited by the slowest processor. And we want to minimize the cost of the slowest processor. So the maximum cost over all processor, we want to minimize it. So we want to find the partitioning and the ordering that will give us this minimal computational time. So this is the second problem. So now, how can we find good solution for these two scheduling problems? So for the first one, it's quite easy. We can use whatever software is available for the traveling salesman problem. So there is two examples. The first one is a heuristic, which is a Lin-Kernighan-Hellsgren method, really efficient. And the second one is the Concord software that encompasses nearly all possible way of computing, of obtaining good schedule for the TSP. For the second problem, it's going to be a bit more difficult because there is no potential, no problem that are identical. So here it was based on this function was based on the vehicle routing problem, but here we don't know anything about this problem, at least from our knowledge. So we designed a genetic algorithm to solve this problem. I will not go into the detail, but the idea is that we just inspired ourselves from some state-of-the-art method from the VRP, vehicle routing problem, and we employed parallelism to make it quite efficient. Okay, so now for the results. So we will start with the simulated DAGs. So we wanted first to validate the method. And for that, we we generated a set of graphs using an existing software. And we simulated DAGs that have like 20, 50, 100, 200 nodes, having different structures. So for that, we use two different methods. The fan-in, fan-out method that can do first expand phase, where you create from one node several nodes, and the collapse, where you take several nodes and you create one. So this is the first type of DAG that we simulated. The second method is the layerable layer approach, where you organize your nodes into layers and then you define a probability of connecting the layers together. So using these randomly generated DAGs, we tried our method, and on the sequential execution, what we could see was that the DAG structure had quite a huge impact. So for DAG that had multiple unconnected branches like binary tree or quaternary tree, the scheduling was highly effective, so it was important to schedule them, to have good schedule for them. But when the DAG had many edges, meaning that it was strongly connected, sort of, it was not really effective. And this is an intuitive way of seeing that is that a DAG that has a lot of edges a DAG that has many edges kind of represents nearly all the time the full computation of all nodes. So the overall performance increase that we have seen by using the scheduling against random schedules. So if we just we take randomly a permutation, we could see that we were 1.3 times faster on average. Against the naive strategy, where we recompute each time all the function, the complete function, we could go from 2 to 20 times faster. And this was increasing with the size of the DAGs. So for parallel execution, here you can see on these graphs, on the y-axis, you have the speedup. On the x-axis, you have the number of processors used. So this is from 1 to 8. The colors mean that the DAG structure is different. It's different parameters for the graph generation method. And the full lines are for graphs with 50 nodes, and the dotted lines are for graphs with 100 nodes. So you can see that depending on the structure, the scaling of this method is really different. And you can also see that when we have more nodes, so for the dotted lines here, the scaling is better. So what's kind of funny is that the effect of the structure of the DAG was the opposite of in the sequential case. Here, when we have a strongly connected graph, it's better for us because we have more work to parallelize. So the scaling is better. And so in this setting, we could see up to 40 times faster computation when using 8 processors and compared to the naive approach. So the sequential naive approach. So now we'll go to the maybe more interesting application, the real application based on evolutionary biology models. So here we compared our method to two state-of-the-art software. The first one is FastCodeML. The second one is IFI, at the task of predicting positive selection in protein coding sequence, so in DNA sequences. And both these methods are using some partial results. So I wrote some because it's not a full DAG. Some have a really simplified DAG, like FastCodeML has a really simplified DAG. And they don't use scheduling. We assessed the results on large data sets, so data sets that had more than 1,000 species, which is quite big, 2,000 parameters, and approximately the DAG had 8,000 nodes. And this was taking about 1 gigabyte in memory. These data sets are quite big, but it's not the bigger that we have that we can use. We could use data sets that have more than maybe 3,000 to 4,000 species. This is an example of a DAG with 60 species. So with 1,000 species, this DAG is way, way bigger. Okay, so for the results, so here you have the speedup. The top graph is for the comparison with FastCodeML. The bottom graph is for the comparison with IFI. Just note that here you have a 10 to the power of 2 and 10 to the power of 3 here. And so the first thing that we compared is our method with random schedules. So we just randomize a schedule and we try the method. So you can see that against FastCodeML, we were up to 200 times faster. And against i5, we were up to a bit more than 1 time. I mean, we were like the same, let's say. Then we compared our method with scheduling and parallel function evaluation. So this is not parallel gradient evaluation. This is just shared memory parallel evaluation of the DAG that represent the function. And we use that because i5 offered this possibility. So as we can see, this is scaling quite poorly. But using scheduling, we're still a bit better than hi-fi. Still, for the case of FastCodeML, we can still go up to 1,000 times faster than FastCodeML. Then we tried with the parallel gradient evaluation. This is what I described before during this talk. So you can see that this method is scaling way better. We go up to 20, 30 times faster than hi-fi and 4,000 times faster than FastCodeML. Then we tried to improve a bit more the scaling by combining the parallel shared memory parallel function evaluation with the MPI parallel gradient function evaluation, parallel gradient evaluation. And as you can see, the scaling is even better now. We can go up to 11,000 times faster than FastCodeML and maybe 60 times faster than hi-fi. So just to see these results in a bit different perspective, so if we take that the time to compute the full DAG is TF, so this is the time that takes to get a full function f of x evaluation, the naive strategy on these data sets that had 2,000 parameters would take approximately 2,000 times TF. And our method achieved 26 time TF with 1 processor and approximately 1 time TF with 64 processor. So it strongly reduced the time required to compute the gradient and evaluate the function f of x. So in conclusion, I showed you a way to design an efficient method to evaluate the gradient of f of x using the finite difference method and exploiting the computational DAG representing f of x. Then we validated this concept on simulated DAGs and a large scale application. So in the paper, there is a bit more study about the theoretical limitation that this method has. For the perspectives, the first thing that we would like to do is to design efficient heuristic to replace the genetic algorithm that we used. So some general heuristic or some more model-based, because we know for the model that we have just studied before in evolutionary biology, we know the kind of graph that we can expect to get. And then we would like to consider, because we didn't do it, to consider the joint scheduling for the parallel computation of the function evaluation and the gradient evaluation. And we think that we could further increase the scaling by doing so. So I would like to thank you all for your attention and the 3 anonymous reviewers for the constructive criticism that led to this article, and also my 2 teams, the teams of the Professor Nicolas Salamin from the University of Lausanne, the team of Professor Bastien Chopard from the University of Geneva. Thank you.
This paper is open for questions or discussion.
Hi, I'm just curious about the perspective to replace the genetic algorithm. So is it just something new, or you already have some kind of idea what you can use to replace the genetic algorithm for your search?
So since this problem is quite similar to the vehicle routing problem or the TSP, we could use heuristics that have been designed for that. So I don't know many of them. I don't know any of them for now. I had more in mind the idea that we know the DAGs for some specific application like the one I've shown. And for this application, we could, I think, easily design a really more efficient way of having correct schedules, at least.